Let's take a few minutes to explore the idea of a linear versus exponential growth. Just kind of get an idea of what these two things actually mean. Now, consider the two functions listed below, which I'm about to write in, show that the growth rate of the linear function and the relative growth rate of the exponential function are both constant. Now, if I take f of t to be a linear function, I'll say 27.5 plus 100t, and then I'm going to take g of t to be an exponential function, maybe 100 e to the 0.07t. Let's look at the growth rates. So the growth rates is really just a derivative. So here f prime of t will be simply 100. That's the derivative of this function. So the growth rate is constant. This is a linear function. So of course when you graph it, and this is not actually this graph, but it's just representative of a linear function. Whoops. In general, it's a straight line, so the rate of change, no matter where you are, the slope is constant. It's the same thing. Here, g prime of t equals 0.07 times 100 times e to the 0.07 t. Now this is what we did a little bit earlier in the previous video. This is my original function. So this is actually equal to 0.07 times g of t in this case. This is not a constant rate of change. So the growth here is non-constant. It definitely depends on what the value of g of t is at a specific value of t. Where over here, pick any t, it doesn't really matter. The growth rate is in fact constant. But this asks about the relative growth rate. Well, the relative growth rate is going to be g prime of t divided by g of t, which in this case is going to be 0.07 times, if I use this form right here, 100 e to the 0.07 t divided by g of t, which is 100 times e to the 0.07 t. Obviously, these cancel out, and I end up with 0.07, which is constant. So the relative growth rate, as I said earlier, is in fact constant for a exponential function, just as the growth rate is constant for a linear function.